Alrighty. So good morning or good evening or whatever time you're watching this. I'm really sorry about missing the lecture. Um, this is mostly on me. Some things got switched around and I didn't check scheduling in time. So I'm really sorry. And I'm actually quite sad because I would have really liked to meet you all virtually. But hopefully I will see many of you sometime soon at a conference or something. So in any case, let's get to the content for today. So this is the third lecture of von Neumann algebras on constructions of von Neumann algebras. So before we begin, we'll just recall that what is a von Neumann algebra? It's some unital star subalgebra of bounded operators on a Hilbert space, which is equal to its own bicommutant or equivalently closed in either the strong operator topology or weak operator topology. And notable examples, so we've seen, for example, in Adriana's lecture that measure spaces, L infinity of x mu is a commutative von Neumann algebra where it acts by multiplication on L2 functions. And two, all right, the obvious choice, a unital star subalgebra of B of H, which is closed in the strong operator or weak operator topology, is B of H itself. And outside of dimension one, this is always going to be a non-commutative example. So 2.1 for H equal to C to the N, and at least two, uh, B of H is N by N matrices over the complex numbers. Uh, I mean, it's true to mention one, too, but the point is that these are some non-commutative examples once on finite dimensional Hilbert spaces. Okay, so we'll discuss each of these briefly, and then we'll spend a large portion of the lecture today on von Neumann algebras from groups. Okay, so I'm actually going to start with item two, uh, and let's get some intuition for general von Neumann algebras coming from matrix algebras. All right. So in the following, I'll fix an n, which is at least two, and we'll discuss some things. So what are the things? First is recall that we have these matrix units. Matrix units. And so for I and j between 1 and n, this is the matrix which has zeros everywhere, right? Zero, whatever, except for a 1, which lies in the ith row and j's column. Okay, so in particular, the span of such things is gives you all n by n matrices over the complex numbers. And in addition, for all I, appropriately in whatever matrix algebra I live in, the diagonal things are a projection. Okay. And if this isn't like immediately, oh yeah, that's definitely true, I encourage you to pause this for a really quick second and recall the definition of a projection and check that this thing is a projection. In particular, so if you didn't pause, then I'm ruining it. In particular, when I square this matrix, it's the same as itself, and that's the same as if I take its conjugate transpose. All right. So there's a bunch of projections, and there's this statement in the notes, which I think in spirit is correct, but as a nitpicky mathematician, of course, I have some, mm, you know, qualms. So I'll ask, is every sum of uh, these EIIs a projection? Okay, Great. And that's a really, really quick exercise. And then a follow-up exercise, which is related. So this one is related to 1.3.1 in the notes. Asks, well, do projections in matrix algebras always span the entire algebra? And in particular, you could check this for some small cases like the 2 by 2 and 3 by 3 matrices. All right, so that's a bit about the existence of projections in matrix algebras. There's one other thing that will motivate some intuition and definitions that will come later in the course. So the second thing is also recall from some linear algebra course or something, the unnormalized trace. So the usual thing that, I don't know, like an undergraduate linear algebra student would think of if I asked them about the trace on the matrices is that the trace of a matrix A is the sum of its diagonal entries. Okay. And in particular, well, what are some facts about this? So, fact one, it's invariant up under cyclic permutation. So if I take some product of matrices and I cyclically permute the elements, then the trace does not change. And in fact, as a subfact of this, up to scaling, it's unique. Up to scaling, trace is the unique linear functional which does this. And I don't mean up to, I mean under. So when you do cyclic permutations, the value of this linear functional doesn't change. And it's the unique thing which does this. And kind of a food for thought question here is if I wanted an actually unique thing, not a unique up to scaling thing, and if I care about, the algebra of n by n matrices, in particular as a unital subalgebra of B of H, then what scaling would I choose on this functional to make it actually unique? And that will come up later when we define a trace, of course. All right, other things about the trace. So fact two, which is fairly easy to see, we can rewrite the trace as the following quantity. I can take the sum over the standard orthonormal basis and compute this inner product where I evaluate against the standard basis and then, take this dot product. Okay, so where this EI is the standard basis, meaning there's a 1 in the ith component and zeros elsewhere. Okay. Moreover, in fact, this formula actually works if I replace EI with any orthonormal basis. So this still works for any orthonormal basis, Fi. All right, and this formula is actually the analog of how we will end up defining a trace for certain operators on infinite dimensional Hilbert spaces. All right, so that's all the intuition that I want to talk about from matrix algebras. The other thing that I would like to discuss is a couple of remarks on that commutative example of L infinity, and then we'll spend most of our time on group von Neumann algebras. So Let's give some remarks on L infinity. We saw this as a star subalgebra of bounded operators on L2 of the measure space during Adriana's lecture. And the first remark is, again, there's lots of projections. So what are the projections inside of bounded functions over a measure space? Well, they're just all the indicator functions. So the indicator function of any measurable set uh, is a projection. And this is very, very different from the C-star algebras case, that you have many, many of these projections because you don't require continuity of the functions. You can just do these little step functions. And of course, when you take sums of these projections, sums of indicator functions on measurable sets, you get all simple functions, which are dense in L infinity. So again, these projections there are so many of them that their span is dense. Okay, and item two also has a trace. I mean, the invariant under cyclic permutation thing is satisfied trivially here because the algebra is commutative, but we also have this linear functional. What is it? If I take f and then I integrate, then this is a canonical way of assigning some value to an L infinity function. Of course, this is only finite if the measure space is finite. So for finite measure spaces. That's not what I meant to do. Sorry. The joys of giving lectures online. All right, for a finite measure space, x mu. And I want to make a little note. Okay, I come a little bit from probability. If your finite measure space was the unit interval, this Lebesgue measure, then this linear functional is assigning the average value, right? The expected value of f as a random variable. Okay, so we see some themes emerging from our basic examples. There's lots of projections. They have some trace. And now we will move on to discuss the third example and the main topic of today, which is group von Neumann algebras. Okay, so for any countable discrete group, we'll construct an associated von Neumann algebra, and then we'll discuss some properties of such an object. This is an introductory thing of an incredibly active area of study. Actually, Adriana, who gave the second lecture, does a bunch of things on super rigidity of group von Neumann algebras, which asks how much does the von Neumann algebra remember about the group and things like that. So very active current area of study, but let's just do the basics today. So first, fix a countable discrete group, gamma. And then define a Hilbert space associated to gamma. So Hilbert space, L2 of gamma. If you're familiar with this, I mean, I guess make the video go faster on your end, but I'll just say briefly, what is this Hilbert space? If I have two vectors in the Hilbert space, these are actually functions from gamma to the complex numbers, of course. So these are some functions from the group to C. Then define the inner product of Xi and eta to be the sum over all group elements of Xi G and eta G with the complex conjugate. So this gives you a nice canonical way of turning, oh, and then obviously you take the completion with respect to the norm induced by this inner product, and then you get a Hilbert space, right? Okay, I should say, I'm being a little bit sloppy. I should say, in particular, these functions have to satisfy the property that they are in L2, meaning that this quantity, this norm is actually a modulus squared, is finite. Okay, great. Okay, and this is really, kind of looks like L infinity acting on L2 by left multiplication somehow. It's the analog of that, but also it's non-commutative when the group is non-commutative. All right, so why do I say this thing is like L infinity acting on L2, but not necessarily commutatively? Well, the way that we're going to make an associated von Neumann algebra is that we have to consider the group acting on itself by multiplication. So consider the left regular representation. What is this? We denote it by lambda. It goes from the group gamma to bounded operators on L2 of gamma. And I say that it acts by left multiplication, which is more apparent in the second definition that I'll write than the first, but the original definition is, okay, how does lambda g act on some vector c evaluated at some group element h? Well, this is c g h, g inverse h. So this looks weird because it looks like left multiplication by the inverse in this format, and this is for all c in L2 and G and H in gamma. But alternatively, this can be rephrased in the following way. How does lambda G act on a basis? So the basis is going to be these delta H's. This is this delta G is indicator of G as a function in L2, meaning in particular, delta G of H is 1 if H is G and 0 otherwise. Okay, so when I act on this basis of indicators of the group functions, then I end up getting actual left multiplication on these basis elements. So I think that the second definition makes a little bit more sense if you're trying to think about left multiplication, but these two things are equivalent. All right, so I have a short exercise here. If you've never seen this representation before, or if you want to work with your basic definitions from the prerequisite notes, the exercise is for every g and g, show lambda g is a unitary and lambda g star, so the adjoint of this as an operator is the same as the left regular representation of G inverse. So in particular, if you combine these two things, then you have to conclude that lambda E is the unit inside of bounded operators on L2 of gamma. So if you haven't seen this, I would encourage you to pause here and just verify this. It doesn't take too long, and it will make you more comfortable with this definition moving forward. All right, so the definition is the group von Neumann algebra. Gamma is, we denote it by L of gamma. This is because we're using the left regular representation here. And this is, you just take the span of the image of this left regular representation and you complete it to a von Neumann algebra by taking the bicommutant. Yeah, so this is a big general class. It can be commutative, right? If gamma is commutative, and it can also be non-commutative if gamma is not. Okay, and an interesting fact that you might want to ask about this, so the group von Neumann algebra remembers whether gamma is abelian or not. That's great. But it forgets a lot of other things. So fact, this is a great exercise, but not incredibly quick. So I would not encourage you to do it right now in the middle of lecture, but maybe later before office hours tomorrow. So fact, which is important, it's also an exercise in the notes to prove this. L gamma is a factor if and only if gamma is an ICC group, where, what do I mean? Okay, well, let's recall, in case we forgot, factor means the center of the von Neumann algebra is trivial. And ICC, this is a new definition. This stands for infinite conjugacy class group. So what does this mean? It means every non-trivial conjugacy class, all right, what's a conjugacy class? For a fixed G, the conjugacy class of G is just the set of all conjugates by other elements in gamma. And this has to be infinite whenever G is not the identity. So that's what I mean by non-trivial. Yeah, maybe I'm repeating myself here. Every conjugacy class, blah, 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 is infinite whenever G is not the identity in the group. Okay, so quick note, some examples of ICC groups are the free groups on at least two generators, and the group of permutations on arbitrarily finitely many elements, which is usually denoted by S infinity. These are in the notes, I won't write them down. And some non-examples include finite or abelian groups. So this is a really nice fact. Later on in the notes, we'll see that L of gamma, in fact, does not always remember much about the group gamma, but like I said, this is an active area of current research. Okay, so we have this group von Neumann algebra, which is formed out of the left regular representation. Earlier, we saw things like our basic examples of von Neumann algebras, matrix algebras, and L infinity functions, have lots of projections and have a trace. This thing also has a trace. L of gamma has a trace. What is it? If I take, so this is some linear functional going from L of gamma to the complex numbers. And if I take in some operator X in L gamma, then the trace looks very reminiscent of that trace formula, except I'm not doing it against an entire orthonormal basis, whatever that would mean in a group. But in particular, this time, the trace tau encodes the group relations. So what do I mean by that? If G1, if some product of group elements was the identity, then the trace of the associated element in L of gamma would be 1. And in particular, the converse also holds. So really, I should be saying this thing happens if and only if this trace condition happens. And that's what I mean by this trace encodes the group relations. All right. At this point, it's very natural to ask, what's so special about the left regular representation? And the answer is, okay, well, it is a special representation in the sense that I have the group acting on itself by multiplication in this canonical way, which is really nice. But you could do the same thing with the right regular representation. So can do the same with the right regular representation. And sometimes this is advantageous. So let's define the same thing. So the right regular representation is rho going from gamma to bounded operators on L2. And how does it act on a vector C evaluated at a group element H? It's C of HG. And this is right multiplication, and there's no taking of inverses. And again, you just do the same thing. You set the group von Neumann algebra R gamma to be the span of the image of the right regular representation completed as a von Neumann algebra. All right, so we have these two ways of defining a von Neumann algebra associated to a group, and well, I actually want to say that they give you the same object. So the main theorem that we will spend the remainder of lecture proving, this is theorem 1.3.7 in the notes, is that if you look at R gamma, it is in fact the commutant of L gamma, and L gamma is the commutant of R gamma. So in particular, when you take the bicommutant of L gamma, you get L gamma back. Yeah, so you have these two von Neumann algebras, and in fact, they're each other's commutants inside of B of L2 of gamma. That's how these two things are related. Okay, great. In order to prove this, we'll need to actually do some work. So the remainder of the lecture will be devoted to proving a couple of results and doing a bit of work. I'm going to skip over some details in the classic way, but I'll try to make kind of a complete picture and tell you which exercises I think are a little bit easier to verify in this picture. All right, so in order to prove this, we need a little bit of machinery. So we have to define the convolution of L2 vectors in L2 of gamma. So for xi and eta in L2 gamma, define their convolution by xi star eta. So this is a new vector in L2. How does it act on a group element G? This is the sum over all H in gamma, CH, and eta of H inverse G. And this looks like the usual convolution of functions, meaning you integrate over a shift. The shift is H here. One of the thing gets evaluated at the shift, the other one gets evaluated at a shifted version of the evaluation at G. Then you multiply and integrate across. Okay, something that we're going to use over and over in the proofs to come. So important fact, I will not reprove this. And I guess I could give it a name, right? Fact star, whatever, for the purposes of this lecture. Note that for all G and gamma, the convolution evaluated at G, the size of whatever this complex number is at most the 2 norm of xi times the 2 norm of G. And this is just, you know, by Cauchy-Schwarz. So in particular, if I look at xi star eta, this object as an object in L2 of gamma, as a function on L2 of gamma, and then I look at its sup norm, then this is also bounded by 2 norm of this product. All right. So now that we have the convolution, let's define some important class of operators. It's things for which this convolution is a bounded operator. So def, we say that xi in L2 gamma is a left convolver if, when I convolve on the left by xi, this is still in excuse me, sorry. Okay, this is still in L2 of gamma for all eta in L2. All right, and you can find the same thing. C is a right convolver if when I right convolve by C, it's in L2. Okay, further points of this definition denote by lambda of C and rho of C. The bounded linear operator, which maps eta to left convolution by Xi and eta to right convolution by Xi. Note that there is no room for ambiguity here. You might protest and say, oh, lambda is the symbol for this left regular representation of the group. And the difference here is, of course, that I'm plugging in something in L2, not something in the group. So it's well understood that when I write lambda of Xi, I mean this bounded linear operator. So this is as, well, they're not always bounded, as linear operators. Yeah, so there's no room for ambiguity. I don't mean the left regular representation because I'm not plugging in a group element here. Okay, all right, so then also you set the left convolvers related to gamma to be the set of all linear operators, lambda Xi, where Xi is a left convolver, and same thing for right. So RC gamma, same definition. Here you use right. Oh, and here you use rho of Xi, of course. All right. Great. Okay, so we've defined these classes of linear operators, left convolvers and right convolvers. And we want some kind of relationship with L gamma and R gamma eventually, these von Neumann algebras. And to get there, well, I need some criterion for when a vector is a left convolver. And the criterion is not too surprising. So I was saying earlier up here that these things are linear operators and not always bounded. And now I want to say, well, when Xi is a left convolver, then lambda Xi is in LC of gamma and is a bounded linear operator and vice versa, right? So this lemma says Xi in L2 gamma is a left convolver if and only if it's bounded, so there exists some constant such that this linear operator in 2 norm is bounded above by C times. And remember, this is this thing here is literally lambda Xi as a linear operator acting on eta. So I am saying that lambda Xi defines a bounded linear operator. Okay, but not only that, I have a little bit of this lemma I haven't finished. So for all finitely supported, so this is a slightly easier condition to check. I don't have to check all eta, just the finitely supported eta in L2. Okay. And the analogous statement for right things hold. Okay, so you can same for right. And I won't rewrite the statement there. Okay, proof. So the only if direction, meaning assume that C is a left convolver, then this thing is bounded, is a consequence of closed graph theorem and the fact that the 2 norm dominates the infinity norm. I'm going to omit this here. It is in the notes, but also it's not too complicated, so I would encourage you to pause here and try to figure out what the proof of the forward direction is. just from these two ingredients. It's a nice little exercise. Okay, but the part that requires a couple more steps, it's still not terrible, is the backwards direction. So in the backwards direction, we assume that we have this boundedness on all finitely supported things, and then we want to prove that C is a left convolver. All right, so suppose that this condition holds. C convolved with eta in 2 norm is bounded above by C times the 2 norm of eta for all finitely supported eta. And then define the following object. So I'm going to write xc because it's related to c. So define xc to be c star eta. Note that xc is actually equal to lambda c as we've defined it earlier, except that it's restricted, right? This is restricted for finitely supported things, but in particular, because of the boundedness, I can extend it. So then xc extends to a bounded operator on all of L2 of gamma instead of just on the finitely supported things. All right, and then the point then for arbitrary meaning not necessarily finitely supported, eta in L2 of gamma. There is some finite subset outside of which eta is small. So what do I mean by that? This is the usual thing. So I have some L2 function, ostensibly. So after some finite set, outside of some finite set, it has small values, otherwise it wouldn't be L2. So for all epsilon, there exists f inside of gamma finite, such that the sum of essentially the L2 norm on eta outside of this finite set f is small. Okay? Then one does the usual trick, meaning like the usual trick from, like real analysis integration, whatever. You should add 0 cleverly, incorporating this finite set f, and then use the fact that one part of it is bounded by this epsilon, and the other part, I have this boundedness because that part is finitely supported, and then I get the thing that I want. Okay, that's the strategy. We do the usual thing. What's the usual thing when we actually write it out? By the way, if that made sense to you, I would encourage you to pause again and then try to write out this argument and finish it for yourself. But okay, for the purposes of the lecture, I will do it. All right, so I want us to look at the difference between C convolved with eta and xc as an operator acting on eta. Yeah, in particular, I want to show c star eta is equal to this extended xc eta on L2 of gamma. All right. Okay, so we're going to add 0 cleverly. And the addition of 0 is going to be via eta restricted to this finite set f. And okay, and same thing. So I add 0 and I do triangle inequality. All right, great. And then I want to say, well, this is the part where I know that the difference is small on the arguments, right? So, well, first, by domination of the infinity norm by the 2 norm, this is at most the same quantity, but in 2 norm instead of infinity norm. Okay, and I have this bound up here on the 2 norm. All right, so what do we get? In the first term, I'm gonna pull out, I'm gonna do the same thing. This is C convolved with, okay, I'll add some extra steps. This is C convolved with eta minus C convolved with eta 1f. Okay, And we saw earlier that the infinity norm of, but by fact star, right? So this first thing is by fact star, eta minus eta 1f2. All right, this guy is by star. Okay, and the second bit is just by the usual inequality in 2 norm, operator norm of xc as an operator, and then the 2 norm of this difference. All right, and now we have what we want, because this bit over here is less than epsilon. That's why we chose the epsilon squared in the estimate above. And so in total, this is at most the norm of xc. Okay, it also appears here, this is also less than epsilon, plus the operator norm of xc epsilon. All right, and now epsilon is arbitrary, so in particular, I can send this thing off to 0, and I get that the infinity norm of this convolution and the, do I have a laser pointer? Yeah, all right. Of this convolution and xc as an operator acting on eta is 0. So, great. C star eta is equal to xc eta is in L2 of gamma. And so lambda c, which is defined as this linear map, which is xc, right, is in LC. Okay. All right, so that's the end of the proof of the lemma. And the lemma says something is a left convolver if and only if it's bounded on finitely supported vectors. We're close. All right. There's one more ingredient that we need. And this is a proposition about what LC of gamma is. So LC gamma is a von Neumann algebra, actually. And I will need this when I prove the main theorem. Okay, and so is RC. Okay, so again, I'm just going to do the proof for the left thing. The proof for the right thing is symmetric, so it's fine. I just want to prove this thing is von Neumann algebra. Proof, and I'm just going to do it for closedness in the strong operator topology. I claim that the rest of it is not too difficult, and I leave it as an exercise. You just have to check that this thing is a unital star subalgebra of bounded operators on L2 of gamma. So we will just check SOT closedness. How will we do that? Let's take a net. Let's take a net converging in the SOT. So suppose Ci is in L2 of gamma, is a net in LC, the left convolvers, such that when I look at lambda, when I look at convolution by these Ci's, it converges to some x in SOT. Okay, and this is in bounded operators on L2 of gamma. So a priori, I don't know where x lives other than in B of L2 of gamma. Okay, note now that if I take lambda Ci and apply it to this indicator function on the group identity, then this converges to x evaluated at this group identity by definition of what it means to converge in strong operator topology. And let me define this to be, oh, this is going to be hard to read in my handwriting. Let me use slightly different notation from the notes and call this chi I and call this chi because my C's and my zetas are not distinguishable when I write them. Okay, so let me call these objects, whatever these vectors are chi I and chi. All right, then whenever I take some eta in L2 of gamma, I can do the following computation. I want to show again that, so here I'll make a note. I want to show that the convolution of Xi with, oh, sorry, of chi. I'm like trying to live change my handwriting, my is equal to x evaluated at eta. Okay, great. So what is this? I take chi, convolve it with eta, subtract x evaluated at eta in infinity norm. I want to show this goes to 0, and we're doing the same trick. Add 0 cleverly, use boundedness. Okay, so this is chi star eta minus, well, what am I trying to use? Well, I have these vectors Ci, which in SOT are some approximation for chi, so I'll add and subtract the convolution of eta against this Ci. All right. And again, by fact star, I have that this is at most chi minus Ci. Oh, I'm so sorry. Of course, these should all be chi's. The chi i's are the approximating things. Okay, chi minus chi I in 2 norm times the 2 norm of eta plus, all right, and then what is happening over here? Chi I convolved against eta is literally lambda of Ci convolved against eta, evaluated, sorry, against eta. So here, in 2 norm. All right, so over here, on these two terms, I'm using domination of the 2 norm plus the definition of chi I as this element against the identity. And over here, I'm using fact star from the beginning of this section. All right, then what happens? This whole thing goes to 0, right? So over here, this guy goes to 0 by definition and the SOT convergence. And over here, this thing goes to 0 by the fact that the lambda of the Ci's goes to x in SOT. All right. So the whole thing goes to 0, and my want to show is verified. It is indeed true that convolution against chi is x. All right, so chi convolved with eta is equal to x eta, which is in L2. And this is for all eta, of course, i.e. lambda of c, which is what chi is, right, is equal to x is in LC gamma. All right, and this proves that LC of gamma is closed in the strong operator topology, and so it is a von Neumann algebra. And now we can prove the theorem, right? Hooray, theorem time. All right, let me reiterate the theorem in case we've forgotten. I just want to say that the von Neumann algebra coming from the right regular representation is the commutant of the von Neumann algebra coming from the left regular representation, vice versa. Okay. This is the main theorem. I'm going to write it in a slightly different order from the way it's presented in the notes, but here's the proof. So, claim. LC of gamma, these left convolvers that we've been working with, are the commutant of RC of gamma, and this is our gamma commutant, and vice versa. So, and the right convolvers are equal to the commutant of the left convolvers are equal to this left regular representation group von Neumann algebra commutant. Okay, then if the claim holds by the bicommutant theorem, R of gamma is R gamma prime prime, right? Bicommutant of R gamma. But the claim tells me that the commutant of the right convolvers, the commutant of this right group von Neumann algebra is the left convolvers. So that's LC gamma prime. And this is, right? And then the second line of my claim tells me that the commutant of LC gamma is the commutant of L gamma. Okay, so we're done. This proves the theorem once I prove the claim. Okay? So I needed to prove the claim, really. And the proof of the claim goes by showing the first thing which appears in the notes. So proof of claim goes by showing L gamma is contained in the left convolvers, is contained in the commutant of the right convolvers, is contained in R gamma prime, is contained in the left convolvers of gamma. All right, and let me label these. This inclusion is 1, 2, 3, 4. All right, so I'm only going to prove inclusion 4, and everything else is an exercise. So 2 is an exercise in the notes, and 1 and 3 follow somewhat immediately. So I'll say follow quickly from proposition 1.3.6. I would encourage you to pause here and think about why inclusions 1 and 3 follow pretty immediately from proposition 1.3.6. Okay. So in particular, I'll just kind of say verbally, if you evaluate the left regular representation lambda on a basis of group elements on these delta G's, then you can show that these are in left convolvers on gamma. And proposition 1.3.6 tells you that LC gamma is a von Neumann algebra. And L gamma is the von Neumann algebra generated by the span of these delta G's. So it has to be contained in any von Neumann algebra which contains lambda of delta G. Okay, great. So now I only need to prove 4. So proof of 4, let's do it. I want to show that if something commutes with the right regular representation, a group von Neumann algebra, then it is a left convolver. So let X be in R gamma commutant. Set C to be X delta E. So this is the vector associated to this operator inside of L2 of gamma. All right, then what happens for G in gamma when I look at X delta G? Well, this is delta G is rho G evaluated on the indicator of the identity. And X commutes with everything in R gamma. So in particular, commutes with rho G. So I can swap them. Okay. And X delta E is this Xi that I've defined. So this is rho G acting on Xi. And this is Xi star delta G. Okay, this last equality looks a bit strange. You just have to check that it's true. So if I take rho G, Xi, acting on H, so for every H in the group, this is CHG by definition of the right regular representation. And on the other hand, if I take this convolution and evaluate it at some h, by definition of the convolution, this is the sum over all k and gamma ck delta g k inverse h. And what is the only time that delta g k inverse h evaluates to 1? It's when k is equal to hg. So this is CHG. So this is true for all h inside of the group. And so this gives you the equality on this side over here. Okay, great. What does this mean? This means that x acting on any of these basis elements, delta g, is the same as convolution by c. Okay. All right. Also, if I look at c convolved with eta in 2 norm, this is x eta. That's what we just proved, right? In 2 norm. And because x is a bounded operator, this is at most the operator norm of x times the 2 norm of eta. And this is for all finitely supported eta. Right, this is just because x is some bounded operator on L2. All right, then by the lemma that we proved, which says that bounded things are in fact left convolvers, we have that C is a left convolver. And this means by definition that lambda of C is in LC of gamma. And we already showed up here, the point of this computation is that x is equal to lambda C. So I started with some x, which it was in commuting position with r gamma, and I proved that x is in fact in LC of gamma. This proves the inclusion 4 here, and this claim here proves, sorry, this chain of inclusions proves the claim up here. And that proves the theorem that I cared about. All right, so that was the crash course into group von Neumann algebras. I'm sorry again that this couldn't happen live in person, but I hope this helps, and I really look forward to seeing some of you in office hours on Friday. All right, thanks, bye.